Hello everyone. Welcome to Controllers Tech. As the title says, this video will cover the memory management in STM32. This is rather a very long topic, so there are going to be few more videos on it. By memory management I mean, the different RAMs available in STM32, the external memories, like SDRAM, eMMC, etc., and also we will see how to use the memory protection unit, aka MPU. These videos will be more inclined towards the Cortex-M7 processors. But you can use the same logic in any other STM32 device also. Today we will start with something very simple, and that is, how can we use the different internal RAMs to write and read data. In this video, I am going to explain a little about different memories in Cortex-M7 processors. And then we will see how can we use these memories to save the data, or load the data from. Now why is this important? Well, one of the main reasons is the DMA. Regular DMA don't have access to the tightly coupled memories, so we can't read or write data into TCM using the DMA. Another reason is the large data buffer. Let's say you want to save some picture data into the RAM, and if the main memory is not enough, we can use the other available memories to do so. You will understand this in a while. Let's take a look at the reference manual. This is the system architecture for H745 series. This is as complicated as it can get, and others will be somewhat easier than this. Here I have highlighted the internal RAMs that are available. As you can see, there are 3 different domains available, and each domain we have some memory, along with other things. In D2 domain, there are 3 SRAMs of different size. In D1 domain, there is a single AXI RAM of 512 kilobytes. We have 2 tightly coupled memories in direct contact with the CPU. And in D3 domain, we have 64 kilobytes SRAM. Tightly coupled memories are of 2 types, data, and the instructions. These memories have 0 wait cycle for the data processing, and that's why they are used for the real-time operations, where we can't afford to delay the processing. Also only the MDMA can access them, and other DMA like DMA 1 or 2 don't have access to these memories. We have some inter-domain buses, where the data can be accessed between the different domains. Like D2 to D1 bus, where the masters from the D2 domain can access the resources in the D1 domain. By masters, I mean all these components, which are placed vertically. These components can access all these resources, which are placed horizontally. We also have D1 to D2 bus, where the masters from D1 domain can access the resources from the D2 domain. Similarly, there are other buses. One thing to note here is that there are buses D1 to D3, and D2 to D3, but not in the reverse direction, so the masters from D3 domain cannot access anything other than D3 domain. And that is the BDMA, it can only access the SRAM 4. You can read more about these buses here. We will take a look at the DMA description. As I said earlier, the regular DMA cannot access the TCM memories, and that's what it's mentioned here. This is where the first reason comes up. Here we have the addresses for the memories. DTCM starts at 2 million, SRAM 1, 2 and 3 are part of D2 domain, and they start at 3 million. We have AXI-RAM at 2.4 million. Let's take a look at some other MCU to understand the difference. This is the manual for H723 series. The system architecture looks pretty much similar to what we saw in the H745 series. There is some difference between the number of SRAMs and the size, but it's not that of a big issue. Now let's see the F76 series. Here the architecture is completely different. It does not have any domains, so that's a relief. Also it have SRAM 1, SRAM 2, and the tightly coupled memories. Also note one thing, we can access the DTCM using the AHBS, which is basically connected to every master. Even the DMA 1, and DMA 2. So I think here we can access the DTCM using those DMA, which was not the case with the other architectures we saw. This is very important, and you should check the architecture of your CPU, to see if the DMA can access these memories or not. Here it is mentioned that DMA surely do have the access to DTCM. I don't have means to test for the F7 related queries, but I will clarify this in the next video. So we saw all the architectures, now let's see the working. I have H745 discovery board. Give some name to the project, and click Finish. Let's clear the pinout first. I am selecting external crystal for the clock. Set up the clock as per your MCU. This PK0 is the LCD backlight, and I like to keep it off. Now in the Cortex-M7, we will enable the instruction cache, and the data cache. Enabling the cache will improve the performance of the MCU by a significant amount, but this data cache is the source of all the issues that we will be handling in these videos. Even you know this, you should still use the cache, and handle the memory issues. The MPU part will be covered later. That's all we need, just the basic setup. I have disabled the M4 core, and I am only using the M7 for now. You can check my another video to see how to do that. Here at the memory details, we can see all the types of internal memories available to us. The RAM D2 is the total RAM in D2 domain, and it consists of SRAM 1, 2 and 3. RAM D3 is the RAM in D3 domain, and that is SRAM 4. You can also check these details in the flash linker script. The main RAM at 2.4 million, and that is the AXI-RAM. Now this is where the things get harder. Here I have the linker scripts from the other MCUs. This one is for the H735, and if you see here, the main RAM starts at 2 million. If you check this address in the manual, you will find that it's the address for the DTCM RAM. This is something we should be worried about, you will know in a while. The RAM D1 starts at 2.4 million, and it's the AXI RAM. And other RAMs are as usual. Even in the F746, the main RAM starts at 2 million. And that's the address for the DTCM again. Now why should we be worried about the DTCM being the main RAM? Let's see this. I am not running the second core, so I will comment out these functions. Let's create a buffer of 1 kilobyte in size. Now I will fill this buffer with some random data. Let's build it. Also pay attention to the used RAM size. It's increased by 1 kilobyte. You can also check the memory details, to know where the buffer is stored. The buffer is placed at the location 2,000,002C. This is not an issue for me, but if you have the H735, this address will be in the DTCM RAM. And that's where you need to be careful. Since the DMA cannot access DTCM, you can't perform any operation on this buffer using DMA. Now we will see how can we change the location of this buffer into some other RAM. To do this, we need to define a section. We'll call it buffer. And put the variable along with it. Now we will modify the linker script, so that this attribute can be pushed into some other RAM. Here align 1 means the data will be aligned in 1 byte format. Like here we have 8 byte alignment, here is 4 bytes. And now push this to RAM D2. You can see here, RAM D2 is used by 1 kilobyte. You can check the memory details to see its location. It's not present in RAM anymore, and here we have it in the D2 RAM. Notice that this is at the beginning of the D2 RAM. But what if we want to save it at some other location inside the D2 RAM itself? We need to modify the linker script again. This time we will use the keyword absolute, and give the memory location here. We need to assign this location to a subsection, and we will call it TX buffer. I am creating one more memory location for the RX buffer. It won't show up just yet. We need to point the variable to that location. And now if you see, we have the TX buff in the new memory location. Let's define the RX buffer also. RX buffer is not showing, because we aren't performing any action to load the data into it. I want to store different data into the TX buffer every time. And now let's copy the TX buffer into the RX buffer. Since we are performing the operations on the RX buffer, it will show up in the D2 RAM. There we have RX buffer in that particular memory location. Let's run this program now. Here I am using only one element of the array, since all of them will have same data anyway. The data is updating every second in both the buffers. Let's check the memory locations now. This is the memory location for the RX buffer, and you can see the data here. It's also updating when the new data gets copied from the TX buffer. I will do one more thing here. This section is for the DTCM-RAM, and let's call it buffer DT. Now let's put the RX buffer in this location. So DTCM-RAM have 1 KB occupied now. Let's run this also. We can check the memory location of DTCM-RAM. Here we have the data, and it's updating properly. Now this is working because CPU can access any memory, so memcopy and memset functions can work on any RAM. But it wouldn't have worked if I try to copy the data using the DMA. I am stressing too much on DMA, and there is a good reason for it. Most of the peripherals, like LCD, SD card, SDRAM, and other will use DMA by default, and that's why we need to be prepared for those conditions, where we simply can't use CPU to copy the data around. This was the case for H745, where the default RAM is the AXI RAM, and even if I simply create a variable, it will be created in AXI RAM itself. But this is not the case for other microcontrollers. I will quickly show an example for F746. Here I have created a project for F746. As you can see, the main RAM starts at 2 million hexa. Now let's try to simply create an array. Here you can see in the memory details, the TX buffer is stored in 2,028 address. And if we check the datasheet, this is the address of the DTCM RAM. Now for some application, let's say we can't have the buffer in DTCM, so we will store it in the SRAM1. Same method will be used here also. This is the address where the TX buffer will be stored. Here it shows up in the new memory location, which is the start of the SRAM1. This is how we can store the data in the different memory locations in the M7 processors. This was the introductory video, and it was an important topic to cover. In the next video, I will cover the DMA part. We will see the limitations, and the solutions. And later in the series, I will cover MPU also. This is it for the video. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.